Hey guys, we are back with the final section of Chapter 10, Section 8, where we will talk about the multiplication rules and conditional probability. Our learning objectives here are to find the probability of two or more independent events all occurring, find the probability of two or more dependent events all occurring, and find conditional probabilities. So each day, a professor picks a student at random to work out a homework problem on the board. If the student is selected regardless of who has already went, then this event is independent. If the student is selected from a pool of students who haven't gone yet, then it is dependent because it depends on who has gone, who still has the opportunity to go. So our first two definitions for this section are independent and dependent. So two events A and B are independent if the fact that A occurs has no effect on the probability of B occurring, meaning it does not matter. A couple more examples of independent events. Excuse me. A couple more examples of independent events would be rolling a die and getting a 6, and then rolling a die and getting a 3. Another example would be drawing a card from a deck and getting a queen, putting it back, replacing it, and drawing a second card and getting a queen. So a key word for an independent event would be when something is being replaced. Okay? Those are independent events. However, we also have dependent events. Two events A and B are dependent if the outcome of A does have an effect on the probability of B occurring. So, as we said before, such as the students, if it's selected from a pool of students who have not gone yet, that's dependent because in order for us to know who hasn't gone yet, we have to know who has gone. So that who hasn't gone depends on who has gone. Some more examples of a dependent event will be drawing a card from a deck, not replacing it. So now we're not replacing. So it's out the way, meaning that everything left in there has opportunity to be pulled. Okay, drawing a second card. Another example would be lottery ball, like the lottery ball tumbler. If you select the lottery ball, don't replace it, and then draw a second ball. Okay, so what happens in the second half depends on what happened in the first half. Okay, so we have our first multiplication rule. When two events A and B are independent, the probability of both occurring is P of A and B is the same thing as P of A times P of B. Okay, probability of A times probability of B. Let's look at our first example. As part of a psychology experiment on perception and memory, colored balls are picked from an urn. The urn contains 3 red balls, 2 green balls, and 5 white balls, giving us a total of 10 balls. 3, 2, 10 balls. A ball is picked from and its color is noted, and then it is replaced. Keyword is being replaced. A second ball is picked and its color is noted. Find the probability of each of these. Okay. All right. So because it says replace, we know we're going to deal with the multiplication rule 1 with independent events. So picking 2 green balls, well, my probability of a green ball is 2 out of 10. I'm going to multiply that by 2 out of 10, and I end up with 4 out of 100, which reduces down to 1 out of 25. Okay. Once again, picking a green ball and then a white ball. So green balls still have 2 out of 10. White balls, I have 5 out of 10. So this gives me 10 out of 100, which reduces down to 1/10. Last but not least, I have a red ball, which is 3 red balls. And then I have green balls, which is 2 green balls. So I have 6 out of 100, which reduces down to 3/50. Okay, so that's the multiplication rule number 1. When the events are independent, meaning that the item is being replaced, okay, it has no effect on probability of B because everything's back in there. It's not changing anything. We just multiply them all out. All right, let's look at our next example. Find the probabilities for 3 independent events. 3 cards are drawn from a deck, After each card is drawn, its denomination and suit are noted and it's mixed back in. It's being mixed back in, meaning it's being replaced into the deck before the next card is drawn. Find the probability of getting 3 kings. Find the probability of getting 3 kings. Okay. What's the probability of getting a king? There are 4 kings, so the probability of getting a king will be 4 out of 52, which reduces down to 1/13. So we're really looking at 1/13 times 1/13 times 1/13. We can multiply those out and we get 1 out of 2197. How about the probability of getting 3 clubs? Okay, same concept where we know that there are 13 clubs out of 52, which reduces down to 1/4. So that's really, we're looking at 3. So that's really 1/4 times 1/4 times 1/4. Okay, where each one of those are a club. Multiply, and we have our final answers. All right. Example 3, according to a January 2016 report on MarketWatch, 70% of college graduates will leave college with some student debt. If 4 graduating seniors are chosen randomly and asked if they have student debt, find the probability that all 4 will graduate with student debt. All right, well, let's first look at the fact that we have 70% students graduating with debt. 70% can be written as 70 over 100 or 0.7. Okay, we're looking at 4 students. So the probability of any one student is just 0.7. Then 4 graduates will be 0.7 times 0.7 times 0.7 times 0.7. And that gives us 0.2401. All right. Our new rule, next rule, the multiplication rule number 2. When 2 events are dependent, the probability of both occurring is probability of A times probability of B, given that A has already occurred. Okay, so if A has already occurred, that means that there is going to be some changing in those numbers, some changes in those denominators, pretty much where our total is. Because if we're not replacing it, then we have one less. Okay, if we're not replacing something, then we have one less. So our first example says an appliance store gets a shipment of 25 plasma TVs. 3 of them are defective. If 2 of the TVs are chosen at random, find the probability that both are defective. Remember, the first TV is not replaced after it is tested. Not replaced lets us know that we are going to use this formula, which is the probability of A. In this case, the probability of A will be just 3 out of 25. That's how many defective TVs we have, times the probability of B, given that A has already occurred. Well, if we started with the 3 out of 25, then now we only have 2 options out of 24. Okay, because there are 3 defective TVs out of that 25 total, the probability of the first being defective has to be 3 out of 25. Okay, so now that we found that first one to be defective, we don't replace it, and now we have 2 sets left, 2 defective sets left out of 24 total. Okay, so we can use the second multiplication rule and multiply those out. We get 6 out of 600. We can reduce both sides by 6, and we end up with 1 out of 100. Okay, once again, as you can see, it's changing because we removed it. Given that A has already occurred, meaning it's not being replaced. You can't put that back in there. All right, next example. 3 cards are drawn from an ordinary deck and not replaced. Not replaced. Once again, we know that we're using rule number 2. Okay, because it's dependent. Find the probability of getting 3 jacks. Okay, well, 3 jacks. How many jacks do we have in the deck of cards? We have 4 jacks out of 52. Okay, so the first time I draw a card, I have the opportunity to pull 4 jacks, right? Next time, I have the opportunity of just 3 out of 51 cards now because it's not being replaced. I want to pull 3 cards. I'm going to do it one more time. This time, I have 2 out of 50. Once again, it's not being replaced, so our denominators are dropping down every time, and so are our numerators. Now I just have to multiply, which I get 24 over 132600. Reduce. Okay, so I'm going to run out of room here. All right, let's look at letter B. Getting an ace, a king, and a queen in order. Well, how many options do I have for an ace? I have 4 options out of 52. Okay, all right, so that first time happens, cool. Now I only have 51 cards left to draw from, but I'm trying to get a king. I still have 4 kings in that deck. Okay, all right. 2 cards have been drawn. Now I only have 50 cards left in my deck. Once again, I'm looking for a queen. I have not pulled a queen, so I still have 4 options. Multiply those straight across. 64 out of 132600 reduced by 8. And I end up with 8 over 16,575. All right, getting a club, a spade, and a heart. Same concept. I'm starting with 52 cards total. Well, how many of those 52 cards are clubs? 13 of them. Now I only have 51 cards left, but how many are still spades? 13, because I didn't pull a spade. Now how many do I have left? 50, but how many are hearts? 13. So this time the numerator does not change, just like in B. The denominator still changes, but my numerator does not change. All right, my last one. I'm looking to get 3 clubs. Okay, now I'm only looking at clubs. Once again, it's out of 52. I have 13 clubs, but because I'm only looking at clubs, once I pull one, I only have 12 left out of 51. Once I pull another one, I only have 11 left out of 50. I do my math. 13 times 12 times 11. 1716, 132, 600, which reduces down to 11 over 850. Okay, so depending on what it is, because these were all the same suits, like in D, it's the 3 clubs. Well, once you pull one, then you only have 12 clubs left. When you pull another one, you only have 11 clubs left. Each time you pull a card, period, you're losing a card. So 52, 51, 50. B did not change and C did not change in the numerator because we were looking at 3 different types of cards. Okay. All right. Moving on, we have another formula. It is called the formula for conditional probability. So we know that to find the probability of 2 dependent events occurring, it's important to find the probability of the second event occurring given that the first has already occurred. We call this the conditional probability of event B occurring given that event A has occurred, and we denote it as P of B given that A. Okay, So the probability that a second event B occurs given that a first event A has occurred can be found by dividing the probability that both events occurred by the probability that the first event has occurred. The probability that both events occurred divided by the probability that the first event has occurred. This is P of B given that A. Okay, so let's do a practice problem for this one. Suppose that your professor goes stark raving mad and chooses your final grade from A, B, C, D, F, or I. This will be our sample space. A, B, C, D, E, E. A, B, C, D, E. That's not what I meant. A, B, C, D, F, or I. So find the probability of getting an A given that, so let's write this out. Probability of getting an A given that you get a letter grade higher than D. All right. So we know what we're looking for. I'm just replacing, that's what this is. Okay. Probability of getting an A given that a letter grade higher than D. So on the top, I'm looking for A and a letter grade higher than D. Probability of A and higher than D. And then I'll be dividing that by the probability of a letter grade higher than D, because I'm only looking at this A portion, which is the given that portion, higher than D. So the top part, this is the grade A and higher than D. Well, the grade A and higher than D is here. So we have our 1/6. And then we're looking at probability of grades higher than D. We have, let's change our color. Probability of grades higher than D will be 1, 2, 3. So that will be 3 out of 6. So this will be divided by 3/6. Okay, P of A and higher than D. So to be A and higher than D will be 1 out of 6. And then to be P of higher than D, it's just 3 out of 6. Okay, so now we have 1 out of 6 divided by 3 out of 6. Keep, change, flip. We get 6 out of 18, which reduces down to 1/3. All right, let's go ahead and look at this last example, example 7. Hate crimes are defined to be crimes in which the victim is targeted because of one or more personal characteristics, such as race, religion, or sexual orientation. Table below lists the motivation for certain hate crimes as reported by the FBI in 2015. Okay, we are going to have to do a little math here. We're going to look at this table. It says find the probability that a hate crime was racially motivated given that it was a crime against persons. Okay, we are looking at our formula from our conditional formula. It says P of probability that a hate crime was racially motivated. I'm just going to put an R, given that a crime was against persons. Crime against persons. Okay. So in this case, we can take, since we're only looking at crimes against persons, we have 3,305. That can be our denominator. We only need to look at that spot. And then we have 2,068 that were racially motivated. 2,068. So technically, I guess we don't have to do that extra. We can just do that, because if we're looking at our formula, let me go back to make sure. P of A and B, so P of B given that A, where A goes into the denominator. So our given that, this is our given that statement. So given that statement goes into the denominator. And that's what we did here. And then we have P of A and B in our numerator, which we are looking at. Oh, yeah, that's right. P of A and B will be racially motivated and a crime against persons. Okay, race and crime against persons. Okay, so we can divide those to come out with a nice clean decimal, 0.609. Okay. All right, so once again, all I did was I took the same information, the same formula that I have here, P of B given that A, where given that A is always going to be in my denominator. So anytime I see given that, I'm going to put that number in my denominator. And then my numerator, I didn't have to do much work because it told us hate crime was racially motivated and a crime against persons. Well, race and crime against persons meet up here, 2,068, and that's how that became our numerator. Find the probability that a hate crime was against property given that it was motivated by the victim's sexual orientation. Okay, all right, given that victim's sexual orientation is at 1,178. So victim sexual orientation total is here. And then it says hate crimes against property, given that it was motivated. So we're looking at property and sexual orientation. So that meets here. Sexual orientation and property, we are at 298. Divide those out and we get about 0.253. Okay. All right. So let's look at these last two. Hope you guys see where I got those numbers from. Once again, the bottom number is that given that. Okay, according to our formula, that's the second half of it. Okay. And then our top number, we're looking at where they meet at on this table, because that's the and portion. That's where they're together. All right, a crime was motivated by either race or religion, given that it was a crime against society. Okay. All right, so because it says or, it looks like we're going to have to do some addition here, just like from section 10.7. Now let's look at what we're looking at. Given that it was a crime against society. So crimes against society is 44, so I know that's going to be my denominator because it says given that it was a crime against society. And then it says race or religion. So let's look at race. Race and crimes against society is 28. And then or religion. Religion was 12 out of that same 44. Because it says or, I'm going to add those together. And I get 40 out of 44, which reduces to 10 out of 11. Okay, 10 to 11. Once again, I got that from a crime against society. The total is 44. That's my denominator for both sets because it says or, I'm going to add them together. Okay, race or religion. Race was here, religion was here. All right, last one. A crime was against persons given that it was motivated by religion or sexual orientation. Okay? Crime against religion or sexual orientation. All right, so now I need to look at adding those two up first. So religion, let's change our color. We're looking at religion or sexual orientation. So our total for religion was 1092. Our total for sexual orientation was 1178. I'm going to add those up first to get 2270. So now that's going to be my denominator. So my given that 2270, once again, because it says given that it was motivated by religion or sexual orientation, and we're looking at a crime was against persons. Okay, so we're going to go back up to our crime against persons, but we're going to look at it for each one. So crime against persons for religion was 361. I don't want to, I'm going to do it like this. 361, crime against persons. And then we have crimes against sexual orientation. 876. So I'm going to add those up. 7, 3, 1, 8, 11, 12. 1,237. So I'm going to put that here on top. Then I can divide those out. Oh, I'll put double equal sign. Put that in my calculator. I get approximately 0.545. Okay. I know, lots of math, lots of rules, lots of formulas, but you have it all right here in your notes. You have it all right here in your notes. This last one, once again, because it was motivated by, given that it was motivated by religion or sexual orientation, that or let us know that we needed to add our religion or sexual orientation to get our denominator. And then our numerator was a crime against persons, but we had to look at them separately for religion and then sexual orientation, add those up. Okay, we weren't thinking about race. And then that will be our probability. All right, we have completed 10.8. Please make sure that you are keeping up with your work, writing down any problems, questions, comments.